Welcome back, everyone. This is part 6 in our series on grounded language understanding. We're going to be talking about neural RSA, which is our combination of the rational speech acts model with the kind of machine learning models that we've been focused on for this unit. And I'm hoping that this draws together a bunch of themes from earlier screencasts and also sets you up, if you choose to apply these ideas in the context of an original system or a final project. I'm going to be talking in a general way about these ideas. They really emerge from the papers that are listed on this slide, and the full references are given at the end of the slideshow. Now, what's our motivation here? Recall that in screencast 4, I presented a bunch of tasks that I claim would benefit from the back and forth reasoning that RSA offers, grounded in specific contexts. And those tasks included discriminative image labeling, image captioning, machine translation, collaborative problem solving, interpreting complex descriptions, especially navigational instructions, and maybe even optical character recognition. And I think we could think of other tasks that we could put into the mold of like the colors in context task and really benefit from the mechanisms that RSA offers. However, as we saw at the end of the RSA screencast, there are some obstacles to doing this. RSA as standardly presented is not especially scalable. It's also not especially sensitive to the kind of variation that we're likely to see in actual usage data in the large-scale corpora that would support these tasks. And relatedly, it just doesn't have any notion of bounded rationality, even though, of course, when humans interact, they're not perfectly rational, even in the pragmatic sense that RSA offers. And there's another dimension to this problem for motivation here, which is that RSA harbors a really powerful insight, and we might hope that we can achieve more impact for that model by bringing in new kinds of assessment for it, taking it out of the psychology and linguistics lab and into the world of AI, and in turn achieve more impact for RSA and maybe show more of the scientific world that RSA has a really powerful insight behind it. But of course, to realize all of this potential, we're going to have to overcome some of those core issues of scalability. And that's what I'll show you here. I think I can offer a simple recipe for doing that and testing out a lot of these ideas. To make this concrete, let's continue to ground our discussion in our core task, which is this colors in context task. Just recall that if you're playing the speaker role, you're presented with 3 color patches, one of them privately designated as your target. And your task is to describe that target in that context for a listener. And then in turn, the listener task is, given the 3 patches and no idea which one is the target, and a speaker utterance, use that utterance to figure out which was the speaker's target. And so you can hear in that description that this is potentially a kind of communication game and would support the back and forth reasoning that is the hallmark of the rational speech acts model. So how are we going to take this task and RSA and combine them? Well, the first step is straightforward. We're going to start with a literal neural speaker. I've given that as S theta up here with literal indicating that it's a base agent. And for this, it's just going to be exactly the natural language generation system that we explored in the earliest parts of this screencast, right? Except now we're going to consume 3 color patches with the target always given in the final position. And then the decoding task is to offer a description. And we can make a lot of different model choices here, but the fundamental insight is that we can now treat this agent as a kind of black box base listener. Instead of having to hand specify a semantic grammar, which would be impossible even for the task the size of the colors in context data set, we now just train an agent and use it to play the role of the base agent. And we can, of course, do the same thing for the neural literal listener. We'll again have some parameters theta, which will represent this entire encoder-decoder architecture. This neural literal listener will process incoming messages as a sequence, and then given some context of colors and a scoring function, make a guess about which one of those 3 colors the message that it had as input was being referred to. And again, instead of hand specifying the lexicon, we just treat this agent as a black box. It serves the role of the literal listener. And from there, the RSA recursion, so to speak, is very easy to apply. Let's consider the base case of a pragmatic speaker. So you can see over here, we're going to use our trained literal listener. And this is the most basic form that the speaker can have. And we've just got now a pragmatic agent that is reasoning about states of the world as inputs and making message choices on that basis. And it's doing that not in terms of the raw data, but rather in terms of how the literal listener would reason about the raw data. So that core RSA insight but we're just essentially using L0 here as the mechanism to derive the speaker distribution. Now, there is one catch here, as we discussed. In principle for RSA, this would be a summation over all messages, which would be completely intractable for any realistically sized language model. What we can do to overcome that obstacle is simply use our trained literal speaker, which I presented before, and sample utterances from it. And that small sample will serve as the basis for this normalization down here. So it's an approximation, but it's an easy one, given that we have this trained agent down here. And in practice, we've seen that it does quite well in serving as the normalization constant. And then the neural pragmatic listeners are even more straightforward. Having defined that pragmatic speaker, to put a listener on top of that is really easy. Again, you essentially just apply Bayes' rule and you get a listener out. And in the Monroe et al. Paper, as you've seen, we actually found that weighted combinations of the literal listener and the pragmatic listener were the best at the colors and context task. And let me just close up by mentioning a few other related strands of work that you might think about bringing in. And what I just showed you is the most basic form of this, but many extensions have been explored. So Goland et al. 2010 is a really early paper in the history of these ideas that is quite forward-thinking. They explore recursive speaker-listener reasoning as part of interpreting complex utterances compositionally with grounding in a simple visual world. And I love the connection with semantic composition. This Wang et al. 2016 paper does even more of that. Pragmatic reasoning helps in online learning of semantic parsers. I mentioned before work by Stephanie Kellex and colleagues on what they call inverse semantics, which is a simple RSA mechanism applied in the context of human-robot interaction to help humans and robots collaborate more efficiently. Connie et al. Extend this to kind of more free-form social interaction by showing that RSA has a role to play in collaborative games. I mentioned before this work by Reuben Cohen-Gordon and Noah Goodman on RSA for translation. Reuben Cohen-Gordon did a lot of innovative work as part of his PhD in the context of RSA. He also explored applying RSA at the word and character level. So removing the approximation that we sample from the S0 speaker to create the denominator. Rather, instead, he applies RSA at every single time step in a left to right sequential decoding step. And that time step could be either the word level or, surprisingly, it was very effective at the character level. And then these final two papers here just show that we could move out of the mode of pre-training the base agents and applying RSA on top, and instead have a mechanism of end-to-end RSA learning, which is more ambitious in terms of learning and model setup, but provides more chances for us to be responsive to the nature of actual usage data while still making good on the central insights of RSA, and with luck seeing some empirical benefits from doing that.